It's science, but not as you know it. The Naked Scientists.
Hello, welcome to this week's edition of The Naked Scientists with me, Chris Smith, and also with Helen Scales, who's here this week. Hi, Helen.
Hello.
Now, coming up in this week's edition of The Naked Scientists, how researchers have used nanotechnology to build better batteries, and these are batteries that are going to last 10 times longer than those which we're using to power iPods and laptops and things. Also, why, when things get more expensive, you like them more, which is good news where my wife's concerned, and also how squirrels are faking it with their nuts. That is, they're not always burying them where you think they are. That's all on the way. Helen.
Thanks, Chris. Also this week we're looking at the problem of climate change, but there's a twist. Rather than talking about the problem, we're going to look at possible solutions, including locking carbon dioxide away underground in coal seams, fertilising the sea to boost the growth of marine plants, and turning carbon dioxide into stone by pumping it into old lava flows. But will these strategies work? Or will they bring with them a whole host of other ecological problems? Plus, we'll be grappling with this weighty question concerning fat and thin cyclists.
All other things being equal, who goes downhill faster, a fat bicyclist or a skinny bicyclist?
So roll on that part of the show.
Thank you, Helen. Boom. So if you've got a question for us about the science of climate change and how to combat the problem, do get in touch. Chris@thenakedscientist.com.
The Naked Scientists podcast, powered by UK Fast, the UK's best hosting provider. On the web at ukfast.net.
Well, let's take a look first of all at some of this week's hottest news stories, and this one certainly got me excited because as a user of laptop computers, I don't get much work done, certainly at the pace I type, before the battery goes flat.
Oh, I know, I hate it.
And
then
you're
big
really stuffed.
problems. Yep.
And so I was really heartened to see that Stanford's Yi Kui this week and his team have come up with a way of making better batteries, and these are batteries that could have a capacity 10 times greater than those which are currently in use and on the market. They've actually used nanotechnology to do this, and they've used a technique called VLS, which stands for Vapor Liquid Solid, which is a way of depositing very fine amounts of material on a surface. They've used a gold catalyst, which makes tiny wires, which are just 1/10,000th of a millimetre across, of silicon. And you can make a forest of these wires and turn those into the electrodes for your battery. And why this is better is because it offers a much bigger surface area for the reaction that makes the electricity in the battery. But also, when these batteries, which use lithium, are charged, when the lithium moves into the anode, the silicon, it normally makes silicon swell up. And this is a big problem because the swelling of the silicon causes it to fragment and shatter. The researchers call this pulverization. And it means that bits of the silicon electrode actually break away and are no longer useful within the battery. So over time, and quite quickly actually, the battery loses its ability to be a very good battery. It can't hold much charge and it doesn't actually last very long. With these nanowires, though, they just swell up like tiny wires. They just bulge and they get 400% fatter, but they don't break off. And they know that because they put samples of the electrode when it was in the charged and uncharged state through a process called X-ray diffraction. And this enabled them to actually physically see these things getting bigger and smaller. And they think this means we will have a stable battery which lasts a lot longer and doesn't have any of the problems of the other uses of silica, where it used to just break apart.
And have we got any idea if this is going to become a very expensive battery, or is it going to be a sort of cheaply developed, commercially available thing? I mean, is there any news on that? Or
Well, inevitably, when something is new technology, it is always more expensive to start with because you have to offset the payback cost in terms of the investment of the research in the first place. But according to the researchers, they think it's just a couple of years away from full-on commercialisation and being available on the shelf. So their prediction is, with present laptop technology, at the rate at which you use energy from these batteries, one battery could last you all day, not just 2 or 3 hours.
Sounds brilliant. Maybe I shall hold out till I buy my new laptop, which I'm looking at. Anyway, I'm sure most of us are guilty of occasionally indulging in an expensive treat, whether it's a new pair of shoes or a bottle of pricey wine, because frankly, a little bit of luxury makes us all feel good. Now, scientists have discovered that this really is the case, and that even if you think you're paying more for something when in reality you aren't, you might still get that same feel-good effect. Now, studies have already shown that advertising and marketing can manipulate customers into thinking perfumes labelled as being exclusive and expensive are actually smell nicer than cheaper perfumes. But now a team of researchers from the California Institute of Technology and Stanford University in the States decided to see what goes on inside our brains when we think we're spending lots of money. Now, they used functional magnetic resonance imaging and basically put volunteers inside these machines to look inside their brains while they were being given glasses of wine. Now, they were told that they were being given 5 different glasses of Cabernet Sauvignon, whereas in reality, there were only 3 types of wine. The cheapest one was about £2 a bottle. Then there was a middle one at about £15 a bottle, and an expensive vintage of about £45 a bottle.
Obviously subscribed to the same taste as you, Helen.
The £45.
With the £2 bottle of wine.
Oh,
yeah.
No, please, certainly 15 for me. But anyway, this cheapest bottle that was actually served twice, once in its original packaging, and then again being basically masquerading as a wine that was worth around £20. And then the most expensive vintage was also served up a second time in the guise of a £5 bottle of Plonk. And it seems that this label swapping trick actually worked. The volunteers said that the cheaper wine tasted much nicer when they thought it was more expensive, and vice versa for the pricier wine when they thought it was cheaper. And it turns out this price tag feel-good factor also has a measurable effect in the brain, because when the volunteers were sipping on these wines that they thought were more expensive, even if they actually weren't more expensive, this increased activity in part of the brain called the medial orbitofrontal cortex, which is thought to be responsible for judging the pleasantness of an experience. And this part of the brain didn't light up nearly as much when they were drinking wines that were labelled as being cheaper, even if they were in fact more expensive.
So the bottom line is you can improve the flavour of your wine if you just put a massively expensive price tag on it. Everyone will enjoy it more.
As long as you won't, obviously, if you know that it's more expensive, but your guests may well. It's a very strange thing. It's a bit like a sort of placebo effect on the human brain, because if we expect things that are costing more, then they will taste better.
That's reassuring. It didn't work for my house, though, when I bought that. I'm still reeling from the effects of that 5 years on. Anyway, this is an interesting story. It's about squirrels and how they fake it with their nuts. Michael Steele, he's at Wilkes University, decided with his colleagues to study how grey squirrels behave when they're sequestering food. And everyone knows that squirrels take food and they put tasty morsels underground, and the idea being that they've got a little cache for the winter. And what they decided to do was to see whether, when the squirrel knew it was being watched, it would behave differently. So they first of all just started watching the squirrels, and they logged with binoculars from a distance where the squirrels put their food, and then they went later and checked which of the holes actually had food in it. It turned out the squirrels were faking it about 10 to 20% of the time. The next study they did, they let the squirrels see them digging up and stealing their food. And in response to this food thieving behaviour, the squirrels responded by several different behaviours. 1, they ate more of the food straight away rather than hiding it at all. 2, they put the food in much harder to find places, such as in holes under trees and stuff like that. But 3, and most importantly, they started faking it much more often, in fact twice as often. 40% of the time in one case, the squirrel was digging holes and making it look like it had buried food when in fact it hadn't. And why the researchers say this is important is it makes squirrels very similar to another species, the scrub jay. These types of birds also hide food. They watch what other birds are doing when they're hiding their food, and if they're being watched by another bird, they sneak back, dig the food up and move it later. So it looks like the squirrels, like the scrub jays, may have what we call a theory of mind, the ability to predict the intention on the behalf of another to steal. And needs confirming, but still very interesting. It just goes to show that squirrels are just as manipulative as us in some respects.
Yeah, clever little creatures. And talking about things that live in trees, our final story for today's show, we're going to return to one that we actually talked about in 2005, and that's about ants that live in trees. And this was a story by researcher Steve Janowiak, who talked to us from up high in the canopy of the Amazon rainforest, where he discovered a certain species of ant that lives in trees that glide down if they fall and can actually clamber back up a trunk rather than having to walk across the dangerous floor of the rainforest. Now he's discovered that the same ants can also make themselves look like pieces of fruit. But not by choice. What's making them do that is a type of parasite. Now, Steve, thanks so much for coming on the show to talk to us. First of all, what are these parasites and what are they doing to these ants?
Well, thank you very much for having me. The parasite is called Myrmeconema neotropicum, and it is a nematode parasite that infects these ants and causes their gaster, or their rear end, to turn bright red.
Why are they doing that? When you first saw this, what did you think?
Well, actually, my colleague Robert Dudley was the first person to notice it, and my other colleague, Mike Kaspari, and I, who works on ants, also kind of thought that Robert probably didn't really know what he was seeing, and this is probably a different species of ant. And then we got it into the lab and opened it up, and out poured these nematode eggs. And looking at the ant and the way it behaved, the natural assumption was that it's somehow attracting or trying to attract another animal to transport those eggs to a new colony. And the bird would be the most logical scenario for that.
How does the red color get achieved, Steve?
It's actually not a pigment or something that's secreted by the nematode itself. It is, as far as we can tell, a thinning of the exoskeleton of the ant. Also, possibly the nematode is sequestering pigment compounds from the exoskeleton of the ant. So probably a combination of those two.
Now, you very kindly sent us some pictures, and if anyone wants to see this, it's incredibly striking. Steve sent us the pictures. They're on our website at nakedscientist.com/blog. If you scroll down the screen, you'll see there's a nice black ant, which is the healthy one, and the one which is not healthy, crammed with parasites, we're told, has got a big, bright red rear end. It looks like a berry.
Exactly, yes, like a berry. And it's by removing the pigment from the exoskeleton, what's left behind is this amber color, and that combined with the yellowish eggs inside and a little bit of sunlight makes it appear bright red, like you see there.
So why are the nematodes doing this? What are they trying to get the ants to do for them?
Well, it's a mechanism for transmitting themselves, at least we hypothesize this is the case, to new ant colonies. If the nematodes were to just infect one colony and live out their entire life there without being transported to a different colony, then they would eventually just go extinct. So the most plausible explanation, the most parsimonious explanation for what we have here is that this is a mechanism for getting those nematode eggs to new ant colonies.
So in other words, a bird would come along and eat that ant by mistaking it for a piece of fruit that it would normally find in the colony. How would the parasite then complete the life cycle and get into more ants?
Well, one of the neat things about this story, and one of the reasons that it seems to fit well with the natural history of the ant, is that these ants collect bird feces very frequently. And so that provides a very easy mechanism for the parasite to get into a new ant colony.
Well, why do the ants want to do that? Doesn't sound like a very nice job, the ant equivalent of a sewage worker.
Well, in a tropical forest, mineral nutrients can be very scarce, and so a lot of things collect bird feces. In this case, the ants are often going after solid parts of the bird feces, and so there's probably a lot of nutrient value in that in terms of undigested insect parts and things such as that. So nobody's quite sure, but that's the running idea right now.
We've heard of previous examples of parasites which have been able to turn one animal or make one animal appear to be another animal. There's a famous example of a snail where it gets infected with a parasite that makes one of its antennae look like a caterpillar, so a bird will eat it. Right. I've not heard of any previous examples of an animal being made to look like a piece of fruit, though, Steve.
This is the only example that we know of, at least for the insects. We kind of have to restrict it. There's a parasite that affects a plant that can make the plant look like something that it's not. But this is the only example that we know of fruit mimicry in an arthropod. And so that's sort of a neat story.
Okay, well, we'll leave it there. Thank you very much for joining us, Steve.
Thank you. It was my pleasure.
That's Steve Vinoviak. He's a researcher at the University of Arkansas at Little Rock, with the first example of a parasite that can turn one animal into another piece of fruit entirely to make it a tasty morsel for another animal, a bird.
Laying the facts bare, The Naked Scientists.
This is The Naked Scientists with Dr. Chris and Dr. Helen. We're going to be talking about solutions to the problem of climate change in just a second. So if you have any thoughts, questions or theories on that, then do get in touch. Chris at nakedscientist.com.
And now let's go over to Ben for the first part of this week's Kitchen Science.
For Kitchen Science this week, we've come to Stewart's Science Specialist School in Harlow, and I'm with Rob and Harrison. All right, lads.
Hiya. You right there?
So what do you think of science experiments?
It's great. There's, nothing more fun.
Absolutely excellent. A lot better than writing in books.
Well, Dave, these people sound perfect for a kitchen science, don't you think?
That sounds good to me.
So what are we doing this week?
Well, this week we're going to find out how a remote control works using a digital camera.
Cool. So will this work with any digital camera, or does it have to be a high-end, high-spec one?
Pretty much any digital camera, webcam, digital camera you use at home, probably even a video camera.
So things like cameras on your phone should work as well?
Yeah, that should be fine as well.
So what particular aspect of remote control? I mean, I know that you press a button, it sends a signal to your TV. That's obvious how it works, but what are we looking at?
Looking at how the signal gets from the remote control to the TV.
OK, so how are we going to show this?
Well, first of all, Rob, if I press a button on the remote control and you look at the kind of black bit at the end, or on this one it's got a little clear circle on it, if I press a button, can you see anything?
Nothing, absolutely nothing.
Nothing at all, no.
OK, well, I've got lots of remote controls at home, but I've never seen anything coming out of them, so I'm not particularly surprised by that, Dave.
No, that's not really the experiment. OK, what I want you to do at home is get a digital camera, webcam, phone camera, whatever you like, point the remote control at it, press some buttons, see what you can see on the display.
So you want to look through the camera at the remote control, have it pointing at yourself, and then just press a button on the remote control and see what happens?
Yeah, that's all it is. Very easy.
Well, give this a go at home. Feel free to let us know if you see anything unusual, and we'll come back to you later on in the show.
Thanks, Ben. So grab a remote control, point it at a digital camera and press a button. Just be careful not to turn the Naked Scientist off while you do it. Let us know what you see. Send us an email, chris@thenakedscientist.com.
Don't forget, we've got our blog running, nakedscientist.com/blog. If you want to just quickly put messages on there or respond to what other people are saying to us here on the programme, then you can do that. You just click the leave message or post reply on that screen. Pat in Lowestoft's got in touch, and he said there was a story in the paper recently where a squirrel buried its nuts and then a blackbird followed along promptly, digging them up and eating them. So maybe squirrels are not as smart as they look. What do you think?
Well, it certainly shows that there's a behavioural response to knowing what to do if you're getting your nuts nicked.
That sounds painful. Now, it's hard to turn on the radio or television now and not to be told to reduce your carbon footprint or be more green and things like that. So that's not the message of this show, though, because we want to talk about not the problem of climate change, but the solution. And on the line now is Margaret Linen. She works for Climos, which is a company based in the United States. Hello, Margaret.
Hello, how are you?
I'm very well, thank you. Your plan is to try to lock away CO2 and solve the problem of climate change by encouraging the oceans to soak up more of it. How does it work?
Well, a few years ago, in studying what controlled the biological productivity of the oceans, scientists found that most of the open ocean far away from land was limited actually by iron. And iron is very insoluble, so iron from rivers precipitates out close to shore. Far away from land, the iron often comes from dust storms that move out far over the sea and then fall into the water. So they did both experiments in the laboratory and observations at sea, and then over the last 20 years they've done a set of a dozen experiments at sea spreading fairly soluble iron sulfate, to see what happened. And they found in every case that there were very, very big phytoplankton blooms. Phytoplankton are the small microscopic plants of the sea. So when the phytoplankton bloom, they make organic carbon out of water and CO2 from the atmosphere. Some of that organic carbon is eaten or decomposes close to the surface, so nothing happens to it. But some of it sinks much deeper into the ocean, where it's protected from exchange with the atmosphere. So the big question is how much of that is sequestered. And that's what the current round of scientific experiments that are proposed are designed to answer.
So what you're saying is that the dead bugs which fall to the bottom of the sea will end up locking away carbon in a form where it won't resurface in the atmosphere, and so in that respect it's almost like turning it back into coal.
Well, yes, the sequestration is not as long-term as turning it back into coal. It's sequestered for periods of 100 to 1,000 years rather than up to millions of years like coal.
So why are you arguing then, Margaret, this is a way of sort of buying us time rather than solving the problem of climate change? It locks the CO2 into a position where it can't cause trouble while we sort ourselves out and get our house in order.
That's exactly right. And not only that, it's not a silver bullet. This will not solve the CO2 problem, but it can help in the same way that every other technology and approach that is being discussed can help with the problem.
Doesn't sound particularly environmentally friendly, though. There must be some possible unforeseen effects of scattering large amounts of iron sulfate, that's quite acidic in itself, onto the surface of the ocean to then create a bloom or a massive growth or a surge in the growth of just one species of marine organisms. There must be knock-on effects of that.
Well, several things. First of all, it doesn't just stimulate one species. It stimulates a whole set of species with time. And we know that both from looking at how this happens naturally. Remember, all of those very large quantities of iron go out onto the ocean all of the time, and that's what actually stimulates the blooms. But that set of questions about what are the consequences for the chemistry and the biology of the ocean are very important. And, of course, the first set of questions is, does this work? Does it really sequester CO2? Previous experiments weren't well designed to answer that question, and so that suggests a new set. And then if it does sequester CO2, then we need to know about the consequences for chemistry and biology, and what do they tell us about the limits to which this could and should be used to draw down CO2. So you're obviously going to have to balance that against the problem of CO2 in the atmosphere, what it does in terms of acidification of the ocean, and so forth.
Now, Margaret, you say that previous tests weren't really kind of conclusive as to whether or not this was going to work. And are you looking at trying to answer that question now? And what are you doing to try and kind of get to that answer?
Well, our company is trying to bring private funding sources to the ocean science community to enable them to answer the questions. What they want to do is have a set of larger area experiments so that they would fertilize areas of the ocean about 100 by 100 kilometers. They want to stay much longer to really observe this whole sequence of activities in the bloom rather than just say, oh yes, phytoplankton bloomed. Then they also want to bring new state-of-the-art sampling gear to the ocean. We didn't have a lot of the remotely robotic autonomous vehicles during the time that the experiments were done. And finally, they want to do a lot more modeling to understand how long the CO2 will remain in the ocean and how soon the ocean will re-equilibrate and pull CO2 out of the atmosphere.
Now, Margaret, Climos is a company, so you must have a business model. How do you expect to make money from this?
Well, if carbon is sequestered, and that has to be demonstrated in a rigorous fashion with measurements, with external observers, with very open data, then the carbon that is sequestered can be sold as carbon offsets on the voluntary market, for voluntary carbon market.
Okay, thank you, Margaret. So this seems like a very good opportunity to bring in Chris Vivian. He's from CFAS, that's the Centre for Environment, Fisheries and Aquaculture Science. I guess that makes you sort of the oceanographic equivalent of DEFRA, Chris. How do you react to what Margaret's saying?
Hello, Margaret. Good to hear from you. Margaret's quite right in many aspects that we still don't know enough about exactly what happens in these situations. There's a large degree of uncertainty and a lot of issues to be resolved. Some of the issues you mentioned, we just don't have answers to at the moment, but the experiments that Margaret's talked about should help to identify those.
So what are the big things? What are the big worries? So you, as someone who's worried about the ocean.
Well, some of the issues that have been raised are, will we change the phytoplankton community in the oceans, for example, by doing repeated experiments of this type? Will we, through putting a lot more organic matter deeper into the water, will we change the oxygen conditions there, reduce the oxygen? Will we change pH? Will we create additional other gases which may have global warming potential? There's some concerns being raised with nitrous oxide.
CO2 goes down, comes up as something different.
Could be nitrous oxide
yeah.
or methane, for example, can be generated by plankton blooms. We don't know enough about those yet to understand whether they are significant. They may be, they may not be.
Let's see if Margaret can offer us any reassurance on that score. What do you think, Margaret?
Well, we totally agree with Chris that those are the issues about, but he raised some that have to do with how much CO2 you can sequester and also what the side effects are in terms of other greenhouse gases, and then those other questions about biology and chemistry. We certainly know that you do change the oxygen conditions in the ocean because that CO2 that falls deep into the ocean is I'm sorry, it's not CO2, it's organic carbon that falls deep into the ocean, and it is changed by combination with oxygen into bicarbonate. So the question is that we need these experiments in order to answer those questions. And so we think that this first phase has to be very carefully designed in order to answer both the sequestration questions and the biology and chemistry affect questions.
So, Helen, as a marine biologist, how does this sit with you? Are you worried? Because we've seen umpteen examples of where if you change one species quite dramatically, you get knock-on effects with other things. We've had huge plagues of jellyfish, for example, because we've removed all the big fish that would have eaten the jellyfish. So what do you think the implications of this could be?
I think you're quite right. I think, to be honest, the implications are potentially huge and we really don't understand them yet. That's the problem with the oceans. They can be so complex, the interactions between different groups of animals and plants. So predicting that's going to be really difficult. You could generally take an approach of you are messing with something that we don't understand, so why do that? But maybe because what we're going to achieve will be important enough to do that. But I think we just don't know. That's the problem.
It's not very reassuring, Chris.
Well, at the moment, I think it's far too early to judge whether this could be a viable mechanism to offset climate change any degree. And certainly the estimates that have been made are that it's probably could only be a relatively minor one. That's not to say lots of minor ones might not add up and, of course, be useful if they are otherwise acceptable. So one could not rule it out at the moment, but I think it's far too early to say that it would be a viable option right now.
What do you think are better options? If this is not going to be something which actually has legs, what do you think we should be putting our resources into?
If we look at what's happening now in a number of countries, various parts of the world, things like carbon capture and storage in subgeological structures is being pushed quite hard by the UK and other governments around the world because they believe there's a lot of capacity for that. Now, some of these things will take quite a bit of time to bring into effect, of course, and there are that's probably the biggest one, and it has the biggest capacity, we think. But it will require a lot of money to get it worked up into a viable and a practical option.
And I know we said we weren't going to talk about the problems of climate change, but I just wondered Chris, what you think about how much this really kind of takes people's minds off the problem of creating carbon dioxide in the first place. And does this kind of make us feel a bit better? If there's an option to kind of mop it up, then we don't have to worry about creating it in the first place.
Well, that is certainly a concern that's been raised by NGOs in some of the international discussions. They feel there is a danger that some countries will see this as a way to avoid doing anything. It's certainly a concern. Certainly governments, I think, view it as just as one means of trying to help deal with the problem. We've got to, in their view, I think, apply a portfolio of all sorts of options, including all of the sort of things we've talked about for energy efficiency and so on, renewables, etc., etc. We need to hit it with everything, really, to try and address the problem.
Because the oceans have suffered quite badly because of the effects of global warming, and they continue to do so. The models predict that they will. The oceans will become more acidic, for example.
You're exactly right. That is certainly probably one of the major effects of global climate change that wasn't fully appreciated early on, is that over a long term we're going to make the oceans distinctly more acid. So we are threatening, for example, the existence of corals in the world ocean. Possibly over something like 100 years there will be great danger we'll have hardly any corals left in surface waters because the oceans will be too acidic.
And quickly, Margaret, when do you see actually the strategy for getting this actually tested and then perhaps into a phase where you're selling carbon credits by seeding the ocean in the way you describe actually working?
Well, I think that we're planning for the first experiment that we would give funding to the oceanographic community to do probably in about a year. I anticipate that we're probably looking at a period of a few years, 3 to 5 years, of experimentation to answer the questions that you've raised and that Chris has raised to see whether this technique is effective, and if so, to what degree should it be used. And I think that one of the very attractive things about it, of course, is that it does actually remove CO2 from the atmosphere, not just limit emissions. And Chris raised the issue of acidification, and it's a very serious one. And we're stuck with that as long as there is all of this excess CO2 in the atmosphere. So, again, this technique wouldn't remove all of it, but it could help.
Chris?
Yes, indeed. I think that's probably correct. Certainly, there's a recent publication in the journal Science by 16 leading scientists in this area of ocean iron fertilisation who've identified a series of issues that need to be addressed before they can, we think it could be justifiable if they're all resolved satisfactorily. And it would seem to me that they are going to take a significant amount of time to resolve. I couldn't make a judgment of how long, but I would certainly think, I'd be surprised if it was less than 5 years, put it that way, would be my personal judgment, but that's just my personal view.
Thank you very much. That's Chris Vivian. He's from CFAS, the Centre for Environment, Fisheries and Aquaculture Science, and also Margaret Leinen, who is from Climos. This is The Naked Scientists with Dr. Chris and Dr. Helen. We're talking this week about solutions to the problem of climate change. In a second, we'll learn how old coal mines and even coal that can't be accessed by mining could provide a useful place to stuff some of that excess CO2. We'll be hearing about that, and also how lava could also be a useful repository. You can pump the CO2 down into lava and it turns literally into stone. If you want to participate in our discussion, you can email us, chris@thenakedscientist.com.
The Naked Scientist Podcast, brought to you by thenakedscientist.com.
This is The Naked Scientist. Now, we've heard about the biological techniques of capturing carbon. Now it's time to move on to the geological methods, starting with the use of disused coal mines, something that we have plenty of here in the UK. So we sent Mira down to London to find out more.
Whilst we're all worried about the increase in carbon dioxide in our atmosphere, another worry is our source of energy for the future. The burning of fossil fuels, which aren't renewable sources of energy, means that as well as increasing the carbon dioxide in our atmosphere, our energy sources are running out. In order to try and kill two birds with one stone, Professor Peter Stiles from the University of Kiel has been looking into using unminable coal seams to not only sequester carbon dioxide, but also enhance the release of methane from these seams. As coal absorbs carbon dioxide twice as readily as methane, when CO2 is piped in, the coal absorbs it readily and the methane is freed and released, therefore providing us with energy as well as preventing CO2 from entering our atmosphere. I spoke to Peter recently at a carbon capture event put on by the Institute of Physics at the Royal Society in London, and I asked him about what his team are looking into to capture carbon from our atmosphere and how they plan on going about it.
Well, we're particularly interested in coal as a particular repository in a slightly different context, in that we are looking at catastrophic failures in mines which emitted methane, but that got me interested in how much gas could be stored in coal. With CO2, it's the case that coal actually likes CO2, and if you actually place CO2 close to coal, it will actually start to absorb it and it will give you more methane. And so you can get a virtuous cycle of actually producing an energy source and then storing the byproducts. So it's that kind of combination of being able to deal with an energy issue and also deal with the CO2 sequestration issue, which really attracts me. 30% of the UK is underlain by coal of one kind or another, and even with our very long history of mining, we've only removed a fraction of the coal. So there is a tremendous amount of coal there which is accessible, and if you go to China, as you know, their main source is coal, and if we can produce technologies which will enable them to actually work more environmentally friendly, then that will be a great contribution.
And how would you actually get the carbon dioxide down there in the first place in order to be absorbed by the coal?
You would usually do this in conjunction with a process called coal bed methane. Now, coal bed methane, you actually drill a hole, and in the old days it would be a vertical borehole. Now it will be a vertical borehole with horizontal wells off it. So it can cover from one single vertical hole a very large area underground. You will then pump water off initially and eventually reduce the pressure enough that methane will come off. Now, you can either have a separate borehole in which you pump CO2, or you can do that for a while and then reverse it. Instead of extracting methane, you start to pump CO2 back in, and then that will release more methane. So I kind of imagine some kind of cyclic process where you actually alternate extraction of methane and injection of CO2.
If we were to do that and take it out of our atmosphere, how long would that be able to help us for?
One thing about coal is that you will store it permanently. You've permanently locked it out because coal actually absorbs the CO2 into its structure. Most of the other sequestration methods are not intrinsically permanent because you're actually just putting the CO2 into the porosity of the rock, and it is possible for it to escape. You know, most oil and gas which is ever produced, we don't see. It escaped to the environment. Coal is still there. You know, it actually doesn't move very far. So it's that permanence which is part of it, as well as the volume.
And has this actually been tested anywhere yet?
Yes, there have been several experiments. The biggest one potentially was a collaboration between Canada and Western China, where they increased the output of gas by about 5 to 6 times over what they did without injection of CO2.
Of all the different processes available, what looks like the most promising one to reduce carbon dioxide in the atmosphere by the greatest percentage? I'm
trying to look at this as a combined cycle, that I'm not just looking at sequestration, I'm trying to look at energy too. If you just look at sequestration, then probably I would guess that enhanced oil recovery, pumping it into old abandoned oil fields or depleted oil fields, would be a very, very useful process. That would have been my guess, because the technology for that is very, very mature. But the main fuel for the future will be coal. And so we actually need to deal with that, not just in the UK but globally, because if we just continue burning coal and do nothing with the CO2, then we're going to all be in trouble.
So there you have it. Whilst we can't purely rely on hiding carbon dioxide from our atmosphere, these capture methods are buying us some time to come up with a new clean source of energy for the future, whilst trying to reduce our impact on the environment in the meantime.
That was Mira talking to Professor Peter Stiles from the University of Kiel about the possibility of using coal mines to increase our energy sources whilst reducing the levels of carbon dioxide in the atmosphere.
Now, I've got an email here from Derek. He says he lives in Belgium. He's listening in Belgium. He says, "Love your show, Chris. Can you help us with the following question? Fluorescent lights are already efficient when they're running, but I've heard that it takes a lot of energy to turn a fluorescent light tube on. So is it more efficient to turn off a fluorescent tube immediately when you finish using it, or is it better to leave it on and then wait until you're more likely to not use it again for a while?" You see what he's saying? You know, is it better to leave it on once it's on, and if so, for how long? Now, in the old days, the older technology meant that these lights did consume a hell of a lot of energy to start, but once they were running, they were more efficient. I think with the new technology they've got as the new sort of starters built into them, they're much better, but I don't know. So if anyone has the answer to that question about the energy consumption, the starting cost of a fluorescent tube, a modern fluorescent tube, I'd be very interested to know.
Excellent. I've got another light bulb question here from Lynn Avies in the UK, who says there's a lot of talk about energy saving through the use of low energy light bulbs, but since a lot of that energy ends up as heat, if we use these low energy light bulbs, are we just turning up our thermostats and using more energy to heat our homes? Which is a pretty interesting question. I don't know. I personally don't know the numbers on this. Has anyone in the studio got any thoughts?
Yeah, I suspect that it's still better to have low energy bulbs, I would guess, because electricity is a very inefficient way of producing heat for space. There are better ways using gas and so on. So I suspect it's a question of efficiency.
I think I have to agree with you there. But it'd be interesting, again, to get any numbers on that. So if you've got any thoughts on that as well, then do let us know.
Now, we've heard about old coal mines as being a useful place to dump our carbon dioxide, but how about old volcanoes? The next guest on is Peter McGrail, and he's from the Pacific Northwest National Laboratory in Washington State, and he's been looking at the carbon-catching properties of flood basalt. Now, that's a type of rock that's left over from when lava flowed out of volcanoes. Hello, Peter.
Good evening.
Thank you for joining us. So what's the basis to this technique? How does it work?
Well, basically, we would be looking at capturing CO2 from a stationary source, like a coal-fired power plant, and then injecting that CO2 deep underground, 2,000 feet to as much as, say, 3 miles below ground. And that CO2 would then enter into a special structure in these continental flood basalts. You have to think of these things the way they were produced. We have these massive cracks that were in the Earth's structure, and these massive lava flows then extruded out of those massive cracks and extended out over many hundreds of miles. And these individual flows would have been separated by hundreds of thousands or millions of years. And what happens is that at contacts between these individual flows, there are cracks, crevices, and bubbles that are present. And this is where the porosity and permeability exists in these continental flood basalts for injection and movement of fluids, including CO2.
So what would you do? Would you put the CO2 down as a gas, or would you dissolve it into the water first and then pump the water through those holes in the lava?
Well, it would go down an injection well as a liquid, and so that liquid CO2 would then enter into the formation, displacing water that was present in the pore spaces and fracture spaces in those interflow zones. And then eventually, the water would then absorb that CO2. And the thing that we found is quite intriguing about these flood basalts is that once that CO2 dissolves in the water, we have very, very rapid reactions that occur between the CO2 saturated water and the basalt, and that CO2 gets converted back into solid rock. Calcium carbonate is the end product. And
so quite literally, it's turning the carbon dioxide into stone.
Absolutely, with no additional energy input required other than getting the CO2 into the basalt formations.
Now here's the killer question. Does it work?
Well, that's a question that we're attempting to answer through some pilot studies that we're just about ready to start. We plan to drill our first pilot well here in eastern Washington State would be March or early April of this year. And then about the summer of 2008, we would be injecting 3,000 tons of CO2 into this, called the Columbia River Basalt Group here in Washington State.
That sounds like a lot, 3,000 tonnes, but putting that in perspective, that must be the output from a big coal-fired station over the course of, a couple of hours?
Of course, depending on size, but yes, that's right. It would be a few hours to maybe one shift in terms of CO2 production.
So how are you going to trace where the CO2 goes once it's in the ground?
A variety of ways, monitoring techniques that we use. There are techniques that we extract fluid samples from depth, and so looking at the change in the water chemistry around our injection well. We also use, they're called geophysical techniques. These are seismic techniques that allow us to actually look at and image the CO2 in the subsurface.
Are there any possible negative effects of doing this?
Well, of course, one of the things that has to happen in any geologic sequestration project is containment of the CO2. And so in these deep flood basalts, one of the research areas that we want to investigate is whether the CO2 is staying in the place that we think it will. And that is, we don't want to have cracks and crevices and fractures that would allow that CO2 to migrate a significant distance vertically. And the computer simulations don't suggest that that's possible, but of course they're just computer simulations. So field work is critical to proving out what we're seeing on our computer models.
And finally, Pete, how much CO2 do you think realistically the world could lock away in this way, assuming you're successful?
Well, one of the things we've done is taken advantage of geological data. The Department of Energy in Washington State has spent almost $500 million characterizing the Columbia River basalts here. And that information database has been extremely valuable to allow us to compute these numbers. And what we see is that kind of conservative estimates would be about 20 gigatons to 50 gigatons of CO2 capacity in just the Columbia River Basalt Group, which in perspective what that means is about 10 to 20 years of all the CO2 emissions from all the coal-fired power plants in the United States. So the capacity is actually quite significant.
Well, we wish you luck, and I guess we'll be talking to you in a year or so to see if it worked.
I'd be happy to join you again.
Thank you very much. That's Pete McGrail. He's from the Pacific Northwest National Laboratory in Washington State, where he's planning on pumping CO2 underground into lava flows to see if it can lock away CO2. This is The Naked Scientist with Dr. Chris and Dr. Helen. We're talking about climate change and how we can offset it, some of the ways to avoid the problem. If you'd like to join in, chris@thenakedscientist.com by email.
Sorting out the sparks from the quarks. The Naked Scientists. For more information, get online at nakedscientists.com.
You are listening to The Naked Scientists. Now, every week we are bringing you a rising star. That's a young researcher from the Cambridge University who will tell us all about the cutting-edge research that's going on there. Now, this week we have Andrew Podson looking at universes that never existed.
If you've heard a recent radio or television discussion about cosmology, you might have heard mentioned that we live around the Sun, a single star in a galaxy of 100 billion. That the galaxy in turn is just one of billions of other galaxies visible to us, and that the vast spaces between these galaxies are constantly expanding. You may also have heard that to fully explain measurements of all this, we need to invoke little understood and mysterious ideas like dark matter and dark energy. Most cosmologists work on ideas like these, which is understandable given how much there is still to comprehend. But to introduce you to my own research, we need to gloss over these problems and think about things differently. It's often pointed out that if the laws of physics differed in the most minute way, we as humans simply couldn't exist. But even given a certain set of physical laws, our existence in the universe is only assured by the initial conditions. Let me explain what I mean by that. Let's say you have a pendulum. If you pull back the bob a long distance and then let go, it's going to swing back and forth. On the other hand, if you carefully put the bob right in the centre of the swing and let go, it just sits there, stationary. It's the same physical system, but we're seeing different behaviour depending on how you start it. The entire universe is similar. It seems possible for it to start in different ways, and only if it starts the right way does it produce life, like humans, later on. As it turns out, this means that, shortly after the beginning of time, the universe has to be highly uniform. One part has to look much like any other, except for tiny ripples, which eventually grow into galaxies. But what would have made it look like that? And what dictates exactly how big those ripples are and what form they take? These are questions to which there are no known definite answers, only possible explanations which themselves are riddled with further difficulties. My own current work looks at types of ripples that might not be ruled out in all of these possible theories, but we know from observations that these ripples were not present. So I'm working on universes which are never going to agree with what we actually see. The idea is that this may shed light on why the universe is as it is, and isn't like it isn't. It's a small part of a large jigsaw, but in optimistic moments, I hope it will help us fit other pieces around it.
That was rising star Andrew Ponson, and we'll be having another young researcher from Cambridge University next week to tell us about their work.
And now it's time for a mighty weighty question for this week's Question of the Week.
Hello and welcome to Question of the Week from The Naked Scientist with me, Diana O'Carroll, for some freewheeling action.
My name's Jennifer, and I'm from Chicago. My bicycling club has been having a debate. All other things being equal, who goes downhill faster, a fat bicyclist or a skinny bicyclist?
Will that extra slice of cake get me to work faster? Let's see what our expert has to say.
My name's Joss Darling, and I'm a lecturer in mechanical engineering from the University of Bath. And the question was, how quickly would a fat person or a thin person cycle down a hill? And that's a tricky one, and it's been thought about for a long time, really, because Aristotle was the first bloke that thought about objects falling due to gravity, and at that time he decided that heavy objects fell more quickly than light objects. Now, later on, people like Newton decided that with gravity, objects fall at the same rate, but strictly speaking, that's only true if you're in a vacuum. And of course, on a bike, you're far from it. And the big issue with the bike is the aerodynamic drag, because if there were no aerodynamic drag, then in fact a fat person or a thin person would end up accelerating down a hill at the same rate. But the point is that with a fat person, assuming that they're not incredibly wide, the aerodynamic drag is going to be less significant in terms of their falling down the hill than a thin person. So ultimately, a thin person's going to end up going slower than a fat person. So if you're in a race, then you want to minimize that aerodynamic drag. And of course, the downside to being fat is that there's always going to be a hill on the other side of the downhill, meaning that you've got to put a lot of work in to get up the other side. So there's always a catch.
Although, as Reuben Walsh noted, a fat cyclist will suffer more air resistance than a thin cyclist, making the weightier individual move more slowly. That is true if, for example, you have one cyclist 3 times heavier than the other, who also has a surface area 3 times greater than the thin cyclist. The fat cyclist would only have this much surface area if he bulked up his volume with hundreds of litres of a massless substance, which isn't very likely. Bobsleigh teams have an upper weight limit. The extra weight can be quite an advantage, and air resistance varies very little between teams. It's also brilliant because all those extra mince pies over the festive season will get me to the pub even quicker than usual. It just might present a little more difficulty on the walk back. So instead of walking, I could take the plane. And instead of the plane taxiing, could it do this?
Hi, my name's Kian from Sydney, Australia, and the situation I've got is there's a plane that's standing on a runway that can move kind of like a really large treadmill. The plane moves in one direction while the treadmill moves in the opposite direction. The treadmill has some sort of control system that tracks the plane speed and tunes the speed of the treadmill to be exactly the same but in the opposite direction. So the question is, can the plane take off?
After that, we'll be sticking with the flying theme and investigating how one might recycle air.
Hello, my name's Tom Gallard from London, and I'd like to ask, how is oxygen made and recycled in the International Space Station?
How must a plane be moving in order to get some lift? And can we make breathable air? Send your ideas and new questions to questionoftheweek@thenakedscientist.com or drop into our forum at thenakedscientist.com/forum.
Well, we had quite a response to this fat, thin cycling question on our forum. In particular, this entry by Charles Palmer, who said, in a practical test whilst out cycling with his daughter, he stopped on a slope of about 25 degrees and they both released their brakes at the same time. And over a distance of about 200 metres without pedalling, he was about 20 metres ahead and his daughter was behind. And she weighs, he thinks, about 3 stone less than he does. They're not fat, either of them, but maybe that weight really does make a difference.
And the person calling themselves Turnip Stock on the forum also said, in the Tour de France in years gone by, some light cyclists used to collect a bottle filled with lead before they began a long descent and then threw it away when they reached the bottom. You'd never catch anyone cheating like that these days, would you?
Fancy listening to The Naked Scientists in your bed, on your way to work, or even at work? Why not subscribe to our podcast? For more information, visit nakedscientist.com/podcast.
This is The Naked Scientists. Now time to go back to Ben and Dave. We left them pointing remote controls at digital cameras. So let's go and find out what they could see.
Welcome back to Kitchen Science. Today we're finding out how a remote control sends its signal using only a digital camera and a remote control. So, Rob, we've given you a digital camera here. If you look through the camera, what do you see? Does everything look pretty normal to you?
Yeah, I can see everyone in the class.
And it looks just like it does when you look with your eyes?
Yep, all the same.
And Harrison, we've given you a remote control. Now, once again, can you have a look at the shiny bit on the end and tell me if you can see anything?
There's absolutely nothing there. It looks exactly the same before and after I push the button.
OK, excellent. So now, Dave, what should people do?
Really easy. All you do is point the remote control at the camera and look at the display on the camera.
So, you two ready?
Yep.
Absolutely.
And Harrison, let us know what happens.
Oh, I can see a little white light. It's flashing. Every time he pushes a button, there's a little flash on the light.
Do you want to zoom in a bit there and see if we can have a closer look?
Oh, now it's purple.
So, Dave, where the signal is coming out, there seems to be a purple flashing light. Is that right, or is this just a trick?
I mean, that is what's happening, and there is actually a flashing light on the end of your remote control, but it's flashing a colour which you can't see. The colour it's flashing in is called infrared. So it's sort of beyond red in the rainbow, and your eyes aren't sensitive to it at all, so you can't see it.
So we can't actually see that light, but the camera can. Why is it that the camera picks it up if we can't see it? Surely they're designed to take photos of what we can see.
It is designed to take photos of what we can see, but it's not quite done perfectly. The actual sensor in a digital camera is called a CCD, it's called a charge-coupled device. And that's sensitive to just about any colour of light. And they put little filters on the top, so there'll be a red filter or a green filter or a blue filter on top of them to pick up the 3 colours of light that we can see. But these filters also let through infrared light. So if this shines through, then it's going to trigger the sensor underneath and it's going to show up on the camera.
So the electronic sensor in there will pick up infrared light that we normally can't see. Does this happen with sort of old-fashioned photographic film?
There's not enough energy in infrared light to expose the film, so it probably wouldn't have much an effect on a film camera.
So what do you think, Rob?
It's great. You don't expect it, because usually it's just nothing, so you don't really realise that there's anything there. But when you look at it closely, you can see how much it is actually working.
And are you surprised to find that there's all these different types of light that your eyes just can't see?
Yes, so people know that eyes are pretty good, but there's so many things that we can't see that other things can.
OK then, Dave, so we've proved that we can definitely pick up this infrared light coming out of the remote using something like a digital camera. But what use is infrared light to the remote?
Well, the remote control has this little light in the end. It's actually an LED, a bit like the red and green little lights which tell you a TV's on or another electronic equipment's on. This flashes on and off very quickly and sends signals, a bit like Morse code, to the TV, which has got a sensor in it which can detect that. So when it flashes in a certain way, it'll know to change to BBC One, BBC Two, whatever.
So it'll flash for a certain signal, a certain pattern will tell it to, say, turn the volume up, but a different pattern of infrared flashes will tell it to do something else.
Yeah, that's exactly right.
Well, fantastic. Well, there you go, lads. That's how a remote control works. What do you think of that?
I think it's really clever, but I don't understand. If the infrared is being picked up by the camera and it's being shown through the screen, how can we see it?
That's actually a really good question. You're not actually seeing infrared coming out of the display because infrared's fooling the camera into thinking that red light and blue light and green light are hitting it. But actually, it's not. So you just see red, green and blue light, which your eyes are sensitive to.
All right, that's really interesting, that.
And Rob, what do you think?
I love it. I'm going to do that at home. My dad's camera.
Cool. Well, I hope you've tried this out at home, and it really is a fantastic thing to see and open your eyes to a world of light that you can't normally see. But that's it for Kitchen Science this week, and we'll be back with more very soon.
Thanks, Ben. That's really cool. I'm going to have a go myself. And if you haven't got a digital camera, then just have a look at thenakedscientist.com/kitchen science, and we'll put a picture up there very soon, and you can see what your remote control signal looks like. There's also loads of other fantastic experiments up there, so just go and have a look and try out at home.
That's nakedscientist.com/kitchen science. Had an email from Wayne. He is a forensic science student at the University of Worcester, says loves our programme, but it's playing hell with actually getting any work done, spends too long listening to it. Naughty boy. Also, Johannes Gunnarsson's written in and said, love the show, listen to every podcast of it. My question is, how many watts is a burning candle? I'm wondering if they make some significant contribution to the heat in the room they're in. I don't actually know the answer to that, so if anyone knows the wattage equivalent of your average candle, I'd love to hear from you. Question here for you, Chris. I know that gasoline-powered cars, and this comes from Tyler, by the way, release harmful greenhouse gases into the atmosphere, so I was wondering if many or all drivers switch to hydrogen-powered cars, would it make a difference to the climate, because hydrogen-powered cars are going to release water when they burn hydrogen and react it with oxygen to make H2O? And if so, what changes could happen?
Well, I think, first of all, the hydrogen itself will come from splitting of water by using energy. So the net effect for the hydrological cycle, I think, will be probably close to zero. The more important aspect is how much energy you're going to use actually to generate that hydrogen itself and how that's generated.
So if you had, say, wind power or nuclear power generating it, so there's no net carbon gain, and you then pulled down took the water out of the hydrogen out of water, it's just no net carbon gain, no net hydrogen gain, is there?
You may change just where things are happening in the hydrological cycle a bit, but the net effect should be zero, I'd have thought.
Thank you, Chris. Helen, for you, Roy in Malden says, do fish always swim anti-clockwise in a round bowl? He's watched his sister's fish and they always go anti-clockwise, but when they're in an oblong tank, they go in every single direction.
I actually have never heard about fish taking one direction or the other in a fish tank, so I think we're going to need some more data to back that up. Fish can navigate, they do know where they're going. Why they'd be swimming only in one direction, I have no idea, but I can imagine keep going round and round in a round one, but they can't in the square one because there's corners and they bump into them. So.
It's also a myth that they lose their memory in 5 seconds,
Absolutely.
Isn't it?
Fish are much cleverer, they've got much longer memories than 7 seconds, so yes. But no, I have no idea. Anyone else got any fish in their tanks, want to let us know what they're doing? That would be great.
Do you think they go a different direction in the northern and southern hemisphere?
That's what I thought. Maybe if they're being flushed down the toilet, which I don't recommend, I must point out.
But some people do that.
They do, and it's really bad. Invasive
fish.
species, they shouldn't do that at all. But no.
Well, I was thinking more it's unkind to the fish, but you're thinking there are environmental consequences.
Absolutely.
Well, look, that's it for this week. Thank you very much for listening to The Naked Scientist's solution to the problem of climate change. We have to say thank you to Steve Janowiak with his amazing ants, to Chris Vivian from CFAS, to Margaret Lynan from Climus, Peter McGrail from Pacific Northwest National Lab, and also our production team, Mira Synthelium, Diana O'Carroll, Ben Valsner and Petro Minch. Have a great week. Next week, we are solving the problem of the flu. See you soon.
The Naked Scientists are sponsored by the Wellcome Trust, the EPSRC and UK Fast. For more information, look us up online at nakedscientists.com.